Welcome to Chapter 9. We're looking at radical functions. So radical functions would be anything that involves a radical sign. So we could have something that looks like this. Because it has a radical sign, this would be considered a radical function. Okay, so we're going to do a lot of things with our radical functions. The first thing we're going to do is simplify radical functions. So again, here's an example of a radical expression, the cubed root of 3x plus 9. And back in section 4.2, what's going to help us in this section is this definition. The nth root of a is also a to the 1 over nth power. So let's say we had something like this, the fifth root of a cubed. Well, that fifth root we can write as a 1/5 power. And then by our exponent rules, we can multiply 3 times 1/5, and we see the equivalent is a to the 3/5. All right, and so when we have a radical sign that's in radical form, and then we also have a corresponding exponential form. All right, so go ahead and push pause. And let's practice writing these in exponential form. Okay, so whatever the index is, remember our vocabulary, whatever our index is, that is our denominator. All right, so the next one, the 9 is our index. So it's a to the 2/9. This next one, remember the invisible index is 2. So we could write this as a to the 7/2. All right, and then finally our last one is a to the n over m. If you want to write yourself a note, you can come back up here. Remember this 3 is called the index. All right, and then if we wanted to fill in some more vocabulary words, this is your radical sign. And underneath, do you remember what that's called? The radicand. Okay, so we're going to begin simplifying. That's the name of the section. We're going to simplify. So let's consider these examples. And to simplify, we're going to write in exponential form and then simplify the fraction. So for instance, well, the square root of a squared, perhaps you remember that that's a. But if we wanted to write it in exponential form, the index is 2, and 2 over 2 is 1. Okay, and we can do this for each one. So we write in exponential form and simplify. Write in exponential form and simplify the fraction. Write in exponential form and simplify. All right, let's pause it and then you guys can try the examples below. All right, so our first one, 3 over 3 is a. A to the 6 divided by the index is a squared. And then maybe you're picking up the pattern, a to the 9 divided by 3, a to the 12 divided by 3. And there you go. Okay, so these were examples. The first row, part A, was examples of perfect squares. Perfect squares have exponents that are multiples of 2. So like a squared, a to the 4th, a to the 24th, any even power. Part B were perfect cubes. Perfect cubes have exponents that are multiples of 3. So like a to the 3, a to the 6th, a to the 21st power, etc., etc., a to the 30th. And then finally, perfect force have exponents that are multiples of 4. Okay, so again, these are important because then we can take like the perfect square or the perfect cubed or the perfect 4 power, respectively. Okay, so let's see Some other examples of simplifying. So let's say we wanted to simplify the square root of x to the 7th. All right, so let's go back up here. When we simplified these, they were all perfect squares, right? Part A was perfect squares and perfect cubes. And we ended up with just a power of a. But this time we're taking a square root, and it's an odd number, so it's not a perfect square. We know we have to simplify it, though, because the index is smaller than the exponent. So let me just write that note. So we know we have to simplify because the exponent is bigger than the index, which is 2 in this case. So 7 is bigger than 2. So we know we have perfect squares in x to the 7th. Namely, what's the biggest even number? X to the 6th. All right, so x to the 7th is x to the 6th. Okay, so this is how we're going to be simplifying this situation. We're going to write it in terms of the perfect square, and then we have a product or a product property for square roots, and so we know we can separate them like this, and now the square root of x to the 6th, 6 divided by 2 is 3. So this solution is x cubed times the square root of x. All right, so let's practice that. Let's rewrite 7 and 8 in terms of the perfect squares, and then use our product property to simplify. Okay, so we're looking for the biggest even number. Square root of x to the 12 is 12 over 2, x to the 6th. All right, again, that intermediate step we can write in optionally. We can rewrite it in exponent form, and then we have our solution. All right, and again, we know we're done because the radical, the index is smaller than, or excuse me, the index is larger than the exponent. And then finally, number 8, we have 1, 2, 3 things to consider. If you want, we can take the cubed root separately of all of these things. Something like this. And then b to the 29th, we can write that in terms of the largest power of 3, which would be b to the 27th. So instead of writing b to the 29th, we can write b to the 27th times b squared. All right, now let's see what happens. Let's see, the cubed root of negative 8 is negative 2. The cubed root of a to the 21st, well, 21 divided by 3 is 7. And then finally, b to the the cubed root of b to the 27th, well, 27 divided by 3 is 9. And then we're left over with a b squared. So this whole thing is our solution. Okay. So let's practice on our own. Go ahead and push pause and come back and check your solutions. All right, so again, perhaps you separated the fourth roots like this. The fourth root of 81 is 3, because 3 to the 4th is 81. A to the 12th divided by 4 is a cubed. And then b to the 28th divided by 4 is b to the 7th. All right, so there you go. All right, and then finally, let's see how you guys did here. You have the 5th root of 64. All right. The 5th root of x to the 39. And then the 5th root of y to the 7th. All right, so let's find all our powers in there. All right, so the largest fifth root in 64. Well, 64, how many powers of 2 is that? I always like to count it from 2. So 2, 4, 8, 16, 32 is your fifth root, and 64 is 2 to the 6th. So 32 times 2 is 64. And again, the 32 is our fifth root. All right, the biggest multiple of 5 and 39 is 35 with 4 copies left over. Again, 35 plus 4 would get us back to 39. So just a backwards exponent rule. And then y to the 5th times y squared is y to the 7th. And now we get our largest perfect power of 5. Okay, so I'm going to take the perfect fifths first and put them out in front. So the fifth root of 32 is 2. The fifth root of x to the 35, we have to look at 35 divided by 5. And then y to the 5th, the fifth root of y to the 5th is just y. All right, and then we're left with a 2, x to the 4th, y squared. And this whole thing is your solution. Okay, so we have to simplify whenever the index is smaller than the exponent. We have to simplify whenever the index is smaller than the exponent. And then I'll write that down because we're going to do something else different. Okay, so notice here, these are all examples when the index was smaller than the exponent. Now let's look at an example where it's the opposite. So here's a different type of simplifying. This one happens when the index and all of the exponents have a common factor. In addition, now the exponent is smaller than the index. So the index is larger than the exponent. Okay, so we're essentially going to take out the common factor. So let's look at this first example. Let's rewrite it as an exponential form. And now 6 to the 8, we can take out that factor of 2. And then let's give them back exponential form. So now it's the fourth root, index is the denominator, of x cubed. All right, so essentially, going from here to here, we take out the common factor. All right, let's go ahead and push pause and do these examples on our own. Okay, so you guys are writing in exponential form, taking out the common factor, and then writing it in radical form. Okay, and there you go. And perhaps you're seeing a pattern. Rather than doing this intermediate step and taking out the common factor, perhaps you're coming at this step, and maybe you're just canceling the common factors of all the exponents and index. So again, as a shortcut, rather than writing everything in exponential form, you're coming through and factoring out the common factor. All right. So in general, let's look at this rule. Let k, m, and n be counting numbers, all right, so positive integers. M and n have no common factors. We want to rewrite this expression with as small as index as possible. So again, what we were doing is looking at the exponent divided by the index, canceling out the common factor, and then rewriting in radical form, where the denominator is always the index. Okay, and then that's what we were saying up above. In one step, you can just take out that common factor and really expedite the whole process. All right, so what have we learned about simplifying? So to simplify radical expression with index n, first we find the perfect nth powers of the radicand, the stuff underneath the radical sign. We take out the perfect nth power by taking the nth root. And then after simplifying, we just want to make sure we can write the radical with the smallest indexes possible. So this means to cancel any common factors in the index and all, emphasis on all exponents. Has to be in every single exponents. All of the constants, all of the variables. Okay, the other thing that we're going to touch on, we're not going to spend too much time on. You'll see in your textbook that we can assume that the radicand is positive. Because let's consider this. So the square root of negative 3 squared, we would not write that it's negative 3. Right? We wouldn't just cancel out the squared sign because we know when we take the radical, it's always positive. So what's really happening is negative 3 squared with parentheses is positive 9, and then the square root of that is 3. So really, if anything, we can say that the square root of negative 3 squared is equal to something like this, the absolute value of negative 3. So when we look at something in general like this, the square root of a squared, a is allowed to be anything, all right? And just in case a is positive, we are going to have to put parentheses around the a, okay? And again, this is only true for even indices. It's only true for an even index. All right, because the cubed root of negative 8, for instance, when our index is odd, cubed root of negative 8 is negative 2. Okay, so in your homework, you'll see stuff like assume the radicand is positive, assume the variables represent non-negative numbers. They're saying that because we don't want to have to take the absolute value in all our solutions. Okay, so we're working with radical functions. And so we're going to do a really basic graph of our radical function. So we're going to take x and we're going to plug it into the square root of x. So would it make sense to plug in negative 4, for instance? Can we take the square root of negative 4? No. So we can't put in negative numbers. So we are going to have to start at 0. And then let's plug in just perfect squares. Whoops. So 1, 4, 9, 16, for instance. Okay. So notice our x values are growing quickly, and then our y values are growing slowly. So let's see what this is going to look like. Okay, so if we're going to graph this, we have the point 0, 0, 1, 1, and then 4, 2, 5, 6, 7, 8, 9, 9, 3, 10, 11, 12, 13, 14, 15, 16, 4. Okay, so we're going to be looking at something like this. I'll just make that dot big. There we go. All right, and then this is the basic shape of our square root function. This time we have a domain restriction, definitely. And the nature of square roots are always positive. So our y value is also going to be greater than or equal to 0. So there you go.